Okay, so last time we derived the von Karman momentum integral equation, and the equation was what? Tau wall by rho u infinity square, that is equal to ddx of theta, where the theta was the momentum thickness, and that was given by 0 to delta u by u infinity into 1 minus u by u infinity into dy, right? So this was the equation, von Karman momentum integral equation, obviously for the flat plate. Okay, so I told the objective behind doing this analysis. So let me tell more about that. So if we consider here again the flat plate, so this is the flat plate, okay, and the flow is there over the plate like this and having a velocity u infinity. So there will be a boundary layer formation like this, right? Okay, so now we have derived the exact solution. Okay, we have derived the exact solution as well as the approximate solution, showing the variation of the independent variables with the dependent variables by scaling analysis. The third approach is to assume some profile. Now you see that if there is a section like this and you assume any profile, so this profile is not the exact profile. Okay, so this is not exact. So what we are doing is we are integrating the profile. In integration, the errors within the function, those will be nullified. Okay, that is, the concept is like this, that if we have a function f, that is some, that is okay, so let us say that the exact function is something like this, but you only know that the slope here is in this direction, and you know also that that what is the point at this particular x naught. You also know that at this particular x1 the slope is something like this and the value is something f naught, and here is f1, and you also know the value f2 here. Okay, you also know that this is f2. Okay, and here it is x2. So now if you assume some curve like this, maybe by straight line like this and this, then you see that even if at each point, if you take any arbitrary point here, then the actual value is this, but the assumed value is this. So maybe you are saying that yes, the error is large, but if you see the area under the curves, then those will be more or less same, because you see that maybe this much area is less. Okay, so this much area is less for the approximated curve, but here the area is more. So it is one example and a totally arbitrary example. So likewise what I am trying to say is integration always nullifies, not absolutely it can nullify, but it at least specify the erroneous nature of the approximated function. Okay, so that is the concept, that we are assuming some velocity profile, but we are integrating the momentum equation and as well as the velocity profile, and we are trying to get some tau wall, because as an engineer I am interested to get the tau wall and thusly the drag. So, and in the previous discussion I also told that you have to assume some u by u infinity or some u as a function of f of eta, where eta is y by delta, right? And this delta can vary with x. So you can assume some polynomial approximation. So if you assume some constant, then only one unknown is there. So this is 0-degree polynomial. Okay, you can assume some 1 degree, that is a naught plus a1 eta. So that is okay. So let me first write all the possibilities. So this is a second degree polynomial, and this is a third degree polynomial, and likewise we can have fourth, fifth, and so on. So you see that it is 0-degree, this is first degree, this is second degree, this is third degree. So here you need only one boundary condition. So number of boundary condition needed to find the constant or to find the profile, because you need to find the constants only, then you can know the profile. So here you need only one boundary condition, and here you need two boundary condition here, and here you need 3, 4, and so on. So more the number of boundary condition you are using, more is the accuracy of the assumed profile. Okay, so that is the preferred way, that you should use as much boundary condition as possible. Sorry. Yes, okay, sorry for the inconvenience. Okay, so now let us take some example. So we are taking a cubic polynomial. Okay, so let us take this one. So we are assuming that u by u infinity is a naught plus a1 y by delta plus a2 y by delta whole square plus a3 y by delta whole cube. Okay, and so for unknown constants we need 4 boundary conditions. So boundary conditions, and what will be those? So firstly, no slip at y equal to 0, u is 0. Then we have at y equal to delta, del u del y is 0. Then we also have at y equal to delta, u is u infinity. Now what can be the fourth boundary condition? See that the differential equation, the governing differential equation was what, u into del u del x plus v into del u del y, okay, equal to nu into del u del y square. Now at x equal to 0, at y equal to 0, u equal to 0 by no slip, v equal to 0 by no penetration. Okay, that means at y equal to 0 this must be 0. So this is the fourth boundary condition. Okay, now you have the 4 unknowns and 4 boundary conditions. This is a very simple straightforward mathematical exercise to find the 4 constants a1, a0, a1, a2, a3. I have done it and I am directly writing the values because there is no meaning to do it again, because it is a very simple mathematical algebraic exercise. So I am just listing the values. Okay, okay, so these are the values, and then the profile becomes this. So if you have solved any gate PIQ or maybe any standard problem from any good book, then maybe you have seen that you are given this profile. Okay, so this is the assumed profile. Now what your task is to calculate theta, right? So to calculate theta, the formula of theta is, if you write in terms of eta, okay, I am doing from the basic steps, 0 to delta u by u infinity into 1 minus u by u infinity dy. So what you can do is, you multiply a delta here, and then and u by u infinity is a function of eta, then this will be 3 by 2 eta minus half eta cube, okay, into 1 minus 3 by 2 eta minus eta cube by 2, and dy, now you have multiplied the delta here, so that will be d of y by delta, and d of y by delta is, what? Y by delta is eta, okay. So here the limits will be eta equal to 0 to eta equal to 1, okay. So then it will be something constant, let us say this a into delta, this theta will be. Now you have to put it into the von Karman momentum integral equation. So tau wall by rho u infinity square equal to d delta dx, because a is a constant, it will come out of the derivative, right? Now you see that tau wall is what? Mu into du dy at y equal to 0 by rho u infinity square, so this will be d delta dx, right? Now you can convert it into del of u by u infinity by del of y by delta into infinity into delta, right, at eta equal to 0. So that will be rho into u infinity square a into d delta dx. So then you will have this into, so let me write another step, this, okay, let me directly put the value. So del eta or dd eta, because u is only a function of eta, so dd eta of what? This velocity profile, that is 3 by 2 eta, 3 eta by 2 minus eta cube by 2, okay, at eta equal to 0 equal to a infinity, and a infinity will be cancelled out, so this will be a infinity a into delta d delta by dx. Now you can see that this will become 3 by 2 minus 3 into eta square by 2, right, at eta equal to 0, so this will become 3 by 2 only. So this will be 3 by 2 mu dx, okay, equal to rho u infinity a, right, delta d delta dx. Then you get what? Delta d delta is equal to, okay, this dx will not be there because I have taken this dx in the LHS. So if you integrate this, then this will be 3 by 2 mu by rho u infinity a dx, you have to integrate this. Then delta square by 2 is equal to what? 3 mu by 2 rho u infinity a plus a constant c, integration of constant of integration, so into x, okay. That means delta square equal to 3 mu x by rho u infinity a plus 2c. Now at x equal to 0, will there be any boundary layer? There is the onset of the boundary layer at x equal to 0, but there is no boundary layer. So at x equal to 0, delta equal to 0, and that gives c equal to 0, right? it is actually at x tending to 0, so that will be mathematically more correct if I say that. So then we get delta is equal to root over of 3 mu x by this thing, okay. And if you further manipulate it, so then root over of 3 by a, and you have mu by rho equal to nu x by u infinity, right. So see, we got the same variation from the scaling analysis, and here we got this constant as 3 by a. Now if you do the integration and find the value of a, then you will find that this will be approximately 4.64. And remember, the Blasius solution was what? The Blasius solution was 5, around 5. So this was the Blasius solution, okay. So see that we got the boundary layer value very close to the Blasius solution, but we avoided the uh, we avoided the hectic steps of the similarity solution. Still we got the value that we were getting by the Blasius solution, and which is an exact solution. So this is the power of the integral solution. So likewise you should find the tau wall, the skin friction coefficient. How can you find the tau wall? You can find it by mu into del u del y at y equal to 0. Now you put, okay, so if you are doing it at the first time, then these things may seem a bit difficult to you, but as you will practice it, you will get a bit comfortable. So then u infinity into delta. Now you put the values, so this will be du by u infinity d eta at eta equal to 0 into u infinity by delta. Now you know this value, and that is nothing but 3 by 2. We got that. So this will be 3 mu by 2 into u infinity. Now you know the variation of delta, so this will be a by 3 into u infinity by nu x. You will find the same structure, okay. That is the tau wall will be I mean proportional to the rex whole to the power minus half, but just the constants will differ, and you will see that those constants. So here the constant is this, actually 3 mu, uh, I think no mu will be there also, okay. So okay, so I am completing the manipulation here for you. 3 by 2 into root a by 3, here the constant is this. You want a rho u infinity square here, okay. So you have multiplied a rho and a u infinity, so do something mu by rho into u infinity, because you have multiplied a rho and u infinity in the numerator, okay. So this will be this, okay. Now mu by rho is nu, so this will be root over of 3a by 2 u infinity rho into u infinity square, and here it will be what, nu root over of nu, okay, by u infinity into x. So that is nothing but the rex whole to the power minus half, okay. And you know that this value of uh, root 3 by a, so this is what we know, that root 3 by a is 4.6, then 3 by 2 into 4.6 is what, 3 into 2.3, right. So 6.9, right. So these are the values. By these things you can find the approximate values of the shear stress, the coefficient of friction, etc. So up till now we have solved for the hydrodynamic boundary layer. How should the velocity profile look like? what should be the expression for the boundary layer thickness. Okay, now let us solve for the thermal boundary layer. So up till now we did not have any temperature difference between the plate and the fluid, incoming fluid, but now let us consider some temperature difference. So now let us consider the scenario of a flat plate, sorry, let's consider the scenario of a flat plate. Let me draw it first. So this is our flat plate and it is having a temperature T infinity, sorry, T, maybe T S T of surface, and the fluid that is incoming, it is having the velocity u infinity and the temperature T infinity. Okay, and the boundary layer, so here now there will be the hydrodynamic boundary layer as I have mentioned earlier, like this, it will develop like this. Okay, so this is the at a distance x we are having, sorry, we are having at a distance x we are having the hydrodynamic boundary layer thickness delta x, that is given by this. Okay, so similarly I am removing these writings to make the drawing clear. Okay, so here what happens, at the plate we have, because of the no slip condition, the zero velocity, and from that up to this height it will reach, up to this height it will reach the u infinity, right, and here it is 0. So now if we consider the temperature profile, what will happen, here the fluid temperature should be equal to the plate temperature, right, and then we will having, so here we will assume that Ts is greater than T infinity. So similarly the fluid layer just above this layer that is adjacent to the plate, that will be having a bit lesser temperature, and here it will be having still lesser temperature, and here it will be having still lesser, and at a particular distance it will be having T infinity, and here it is having Ts. So now if I join the profile like this, then this is my temperature profile. Okay, and similarly if I, at any other section, if I draw the profile taking any other color, maybe with this. Okay, so now this is Ts, and from the same logic, okay, it will have a profile like this, and here it will be T infinity. Okay, and if we join these profiles maybe by this color, so at any section x, again we take any section x, we will be having a thermal boundary layer. Okay, we will be having a thermal boundary layer delta Tx, and this was delta x, that is hydrodynamic boundary layer. Okay, so here what will be the case actually, I mean if I ask you the same question, that at the same y, if I consider at a particular y distance, okay, so here the temperature value and here the temperature value, what will be, I mean which temperature will be more? By your common sense, you should answer by your common sense. You can just pause the video for a few seconds and then think and then answer to yourself. So the answer will be that, see, the fluid has entered more in this section. Okay, so the plate is having a greater temperature than the fluid, so its work is to heat the fluid. So more the fluid will enter into the plate, more it will be heated. That means if I consider this as TA and this as TB, obviously TA is greater than TB. Okay, and that is why, so I am having a higher temperature Ts and I am having a fixed lower temperature T infinity. So if now this temperature decrement from, so we know that Ta is greater than Tb, that means minus Ta is less than minus Tb, that means Ts minus Ta is less than Ts minus Tb. So for the second case, let us name these sections as section A and section B. So for section A, at the same y distance, at the same vertical distance, I am having lesser temperature decrement. That means, to have, in other words, that is meaning that if I want to have a same temperature decrement in both the sections, then it will take a greater vertical distance for section A. I hope I am clear on this, and that is why the boundary layer, for I mean the thermal boundary layer, is also growing like the hydrodynamic boundary layer. Now you see that, so I am just removing all the unnecessary points. Okay, so I am also removing these things. Okay. Okay, so, and let me draw this delta T with any other color, maybe by this blue yellow color. Okay, so this is delta T, delta subscript T at any x. So here this is the thermal boundary layer, this is the thermal BL, and here this is the hydrodynamic BL or the velocity BL, correct? Now I ask you a question, that is it necessary that the thermal boundary layer will always be above the, I mean the thermal boundary layer edge will always be above the hydrodynamic boundary layer? So that is not the case always. Okay, we can have a second case where we will have this as our delta T. Okay, this as our delta T, we can have this. So we can have both the cases, that delta T is greater than delta and delta T is less than delta at any x, at any x. We can have both of these cases. Now just tell me that which fluid, which fluid property will govern the delta and which fluid property will govern the delta T. So delta is what? Delta is the distance up to which viscous effects are important, right? And viscous effects are propagated by mu. Okay, so let me write these things in a few words. So delta is the distance up to which viscous effects are important. So up to delta, the wall will be able to slow down the fluid, and it does this by mu, that is viscosity. But now you tell me, if the fluid is having a greater inertia, then the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the wall will not be able to slow it down. Then it can, for a fluid, the w which will not be having that much amount of inertia, right? It is the concept like that, that if someone is uh, coming at a faster speed towards you, and your job is to hold his hand, okay, I mean you have to hold him while he is running, and your job is to stop him. But if that person is having a greater velocity, or a greater momentum, or a greater inertia, if that person is having a greater inertia, then maybe you will not be able to stop him. Or even, I mean, maybe you can slow him or her down by holding his or her hand, but you will not be able to stop him or her. On the other hand, if the same person is coming with a slower speed, then maybe you will be able to stop that guy, right? So now the same concept is for the fluid also. So here the competition will be uh, between inertia force and viscous force, right? So if the inertia force is greater, okay, then you have to put some more effort to stop him. So at a particular y, you will not be able to slow him down, okay. And if the viscous force is more, then the velocity will be much lesser, right? So at a at a particular y, at a particular y, okay, let us say at this point, if the inertia force is more, then here the velocity will be more than the case if the viscous force is more. And if the viscous force is more, then it has slowed it down, okay. Then here the velocity is much lesser than the free stream velocity to infinity, and the boundary layer will be thicker, because here the velocity is lesser, is too much lesser, and to reach to u infinity it has to the velocity profile has to go through a larger vertical distance. But if the inertia force is greater, the inertia force, then at this point the velocity will be greater. That means the difference between this velocity and u infinity, that will be lesser, so it can reach the free stream velocity at a lesser vertical distance. That means if inertia force is greater, then my delta will be lesser, and if inertia force is lesser, then my delta will be greater. But not only with the inertia force, it will also depend on the viscous force. Now you think, if the viscous force is greater, then at the same y the velocity will be lesser, and the difference between the u infinity and that velocity, that will be greater. So to reach u infinity, it will have the velocity profile has to grow up to a larger vertical distance. That means if the viscous profile is greater, then the boundary layer thickness will be greater. If the viscous profile is lesser, then the boundary layer thickness is lesser. So that means boundary layer thickness is proportional to the viscous force, but is inversely proportional to the inertia force. And inertia force means it will be inertia means mass into acceleration basically. So it will be proportional to the mass, and mass per unit volume is density. So boundary layer thickness is dependent on the kinematic viscosity. Similarly, now if we talk about the delta T, okay, so delta T is thermal boundary layer, okay. So we know some property that is called K, thermal conductivity. So K of fluid, okay. Now if K is more, now we are having this T is greater than T infinity, then by conduction the heat should flow in this direction, right? by conduction the heat should flow in this direction from the plate to the fluid, right. Now if the thermal conductivity is more, then more and more heat can be propagated, and at a particular y the temperature will be greater, right, because the work of plate is to heat the fluid. So if the heat conduction is very good because the fluid is having a very good thermal conductivity, then at a particular y the fluid will have a greater temperature. Okay, that means at a particular y if the temperature is Ty, so this Ty minus T infinity, I mean because T infinity is lesser, so Ty minus T infinity that will be large, right. So if Kf is large, then delta T will be also large, because Kf is large, that means at a particular y the temperature will be large. So to reach the T infinity the temperature profile has to be longer in the vertical direction. Okay. Now rho Cp, okay, that is the specific heat per unit volume. So it says what? Specific heat says to, I mean, store the heat, right. So ultimately we have something called thermal diffusivity alpha, and that is defined by Kf alpha f of the fluid, not the solid, by K by rho Cp. Cp is the specific heat at constant pressure, right. And basically we can have K by rho C for a fluid. Okay. So this is the thermal diffusivity. Thermal diffusivity means how much the medium will let the heat to propagate. Okay. So if so, how much heat can propagate, right. So if alpha is more, then more and more heat can propagate. That means at a particular y that the temperature will be higher. That means that temperature minus T infinity that is also higher. Okay. So to reach the T infinity the temperature profile should be longer. So if alpha f is larger, delta T also must be higher. Alpha f is lower, that means delta T is lower. Okay. So alpha f is proportional, so delta T is roughly proportional to the alpha f. Okay, so this is the proportional sign, don't confuse it with alpha. So these are not actually proportional, I mean mathematically proportional, but uh, I should say that delta T is dependent on alpha and delta will be dependent on nu, right. So delta by delta T, that will be governed by the ratio of, okay, what, nu by alpha, and that is called Prandtl number. So this is the Prandtl number. Okay. So Prandtl number is a measure of momentum diffusivity and measure of the ratio of I should say measure of ratio of momentum diffusivity to thermal diffusivity. Okay. So this is the Prandtl number PR. Okay. So this is very important to understand the Prandtl number and why it is so, and at the same time you should understand the significance of nu. Okay. and also the significance of alpha. So all these non-dimensional numbers and the properties, you have to understand the significances. Okay, so those are very important. Okay. Okay, so now having told that, now let us solve for the delta t. How can we find the delta t? Okay, so before that I have told you, but let me uh, recapitulate that what is the objective of an engineer, that is to calculate, I mean for the from the point of view of heat transfer, that is to calculate the heat transfer coefficient H mainly. Okay, and also that the temperature profiles, how much heat flux is going, and that will be I mean dependent on this H. So mainly this heat transfer coefficient of heat transfer coefficient. Okay, and also the temperature profile. Okay, so now let us see that how can we calculate that. So I have introduced three different methods. Same three different methods will be applied here also, but now as you know the basics of all those methods, now I can go a bit faster. Still, if you have any doubt and if you feel that I am going much faster and if you are feeling uncomfortable, then you should always tell me in the comments. Okay, then I will adjust my speed according to that. So let us now write the energy equation. So assumptions are uh, constant constant property Newtonian Stokesian fluid, obviously homogeneous isotropic, all the assumptions that we have considered during the derivation of the Navier-Stokes equation. So energy equation, and I will write the Cp form here. So that will be what, rho Cp, okay, del T plus u del x plus v del u del y plus w. I'm sorry, I am writing energy equation. So T del z. Okay, so that will be equal to minus grad of k into minus divergence of k into grad t. Okay, and then we will be having the viscous dissipation term. Okay, and then we will having beta t, okay, dp dt, and another term that is heat generation, right? So if that is correct, now we take some assumptions that viscous dissipation is not important, and and for incompressible fluid this beta is 0. Okay, constant property fluid. So if you have forgotten, then beta is isothermal compressibility. So it will be a function of the change in density. So because I have considered the constant property fluid, that is why beta is 0, because the density will not change and we are not considering any heat generation. So no heat generation. Okay, no heat generation, constant property fluid. And this viscous dissipation, you will get to know that this viscous dissipation will be dependent on what, the velocity gradients. So here the velocity gradients is not very sharp. Okay, so that is why we are neglecting here the viscous dissipation, and also it will be dependent on some dimensional, sorry, some non-dimensional numbers. Okay, so if we non-dimensionalize this, that I will show in the later parts, then some numbers like Eckart number, that will be here. So if Eckart number is much less, then we can neglect the viscous dissipation. Okay, so here we neglect the, we simply neglecting the viscous dissipation. Okay, so and we are having the 2D flow, so no W, so here 2D flow, and so this term will boil down to what, for a constant k. Okay, so this will be plus actually, so k into del 2t del x square plus k into del 2t del y square. Okay, now considering steady state, this is also 0. So you should always take this approach that you start from the most basic thing you know, and then you start formulating the problem. Okay, so never mug up the final equation, because if then the problem may be slightly changed, and then you will be into trouble. So don't go for that approach. I have told in my several of videos that always try to understand everything and approach any problem from the most basic step. Okay, and apply your intelligence, apply your assumptions, apply the facts that are given in the problem to formulate and solve the problem. So then this becomes what, rho, the equation becomes u del t del x plus phi del t del y is equal to, so k by rho Cp, that is alpha, so this plus this. Okay, so now our first approach will be what, order of magnitude analysis or the scaling analysis. Or the other name is scaling analysis, right? So now see that I have told you that we can have two cases. So case 1, that is delta greater than delta t, and it can happen only when, so nu by alpha is greater than 1, that means Prandtl number is greater than 1. So first we will consider something delta greater than delta t. Okay, so let me consider first delta less than delta t, because that will be a bit simpler. Okay, so Prandtl number less than 1. Okay, so now if I draw the case roughly, so this is the flat plate, and if this is my boundary layer thickness, hydrodynamic boundary layer thickness, so this is delta. Okay, so I have told that delta is less than delta t, right? So delta t will be something like this. So this is delta t. Okay, so you see that here we can assume that most of the part inside delta t is outside of hydrodynamic BL. Okay, most of the part inside delta t is outside of hydrodynamic BL. And if I assume this, then from this assumption I can directly say that u, that is the x component of velocity inside delta t, will be approximately equal to u infinity for all y, for all y comma x. Okay, that is because I am considering that, that is, this part is much greater than this part, although it not seems like that from the diagram that I have drawn. But if I draw this as maybe m and this is n, so I am considering that m is much greater than m, and in this part, in all over this part, I have the velocity u infinity. So u inside delta t is u infinity, that is my consideration. So now let me write my energy equation, the modified energy equation that I have derived considering all the assumptions. So u delta t delta x plus v delta t delta y is equal to alpha delta t plus alpha this delta y. So what will be the scale of y? That will be here delta t, not delta, because we are analyzing the thermal boundary layer, not the hydrodynamic one. And x will have the range of L if my this length, the length of the plate is L. And then let us say that T is some Tc, okay, some characteristic temperature that we don't know, okay. And also you will be having u infinity, a scale of u infinity inside the delta t, okay. And we don't know v, but from continuity equation, okay, so let me write the continuity equation here. So uh, sorry, del u del x plus del v del y, that is equal to 0. So if I write u infinity by L is of the order of some vc, characteristic velocity, by delta t. So here vc will be of the order of u infinity delta t by L. So if I now consider the order of magnitude of this term, so it will be u infinity into Tc by L, and this will be Vc into Tc by delta t. But Vc by delta t is of the order of what? This term is of the order of u infinity by L. So total RHS is of the order of the, sorry, LHS, right? Not RHS, it is LHS. Total LHS is of the order of u infinity Tc by L, right? And this thing, this will be of the order of this alpha del 2 t del x square alpha Tc by L square, and this will be of the order of alpha Tc by delta t square. So you can see from these two terms, as delta t is much less than L, delta t square is also much less than L square. That means what? Alpha delta Tc by delta t square is much greater than alpha Tc. So therefore uh, we can, sorry, therefore we can neglect this term. This term we can neglect, 0, okay. Okay, so then the equation becomes what? Okay, we have already neglected this term. So LHS becomes what? I mean RHS. Right hand side is scaling with alpha Tc by delta T square. That means LHS has to compete with RHS. So U infinity Tc by L is competing with alpha Tc by delta T square. So Tc is cancelling out. That means delta T square is having a range of what? U infinity, sorry, U infinity will be in the denominator. So alpha L by U infinity, right? And we can write this number as alpha by nu into nu L by this. Now what we can do is, you can multiply an L here and this will be L square. So that means delta T by L square, I am taking this L square in the LHS. So this will be of the order of alpha by nu, or let me write it, nu by alpha whole to the power minus 1 into U infinity L by nu whole to the power minus 1. So these two numbers, now we know that this is what? Prandtl number whole to the power minus 1, and this is Reynolds number L in of the, I mean Reynolds number in terms of L. Okay. So that means delta T is having a order of magnitude of this minus half REL whole to the power minus half. So we also got something like this in the hydrodynamic boundary layer, and that was delta is proportional to L REL whole to the power minus half, that we got. So here you see that delta by delta T is proportional to Prandtl number whole to the power minus half. Okay, not minus half, it is plus half. Okay, so you see that I told that this Prandtl number is a measure of this delta by delta T, but not it is the case that delta by delta T is absolutely proportional to the Prandtl number. Here it is Prandtl number to the power half, and we can have also Prandtl number to the power any number. There are some well established correlations. Okay, now you apply some energy balance at the wall, and before that let me talk about a very important concept. Many interview actually ask this. So if this is my flat plate, okay, and the fluid is flowing from this direction, so just at the adjacent to the plate, these will be my fluid molecules, right? So by the virtue of no slip condition, I will having these molecules at rest. So at this layer this U is 0 because the plate is also not moving, and here I am supplying some heat, some Q. This Q can be varying with X, this Q can be constant with X. But here the fluid molecules are not moving, then you cannot say that the mode of transfer of heat from the plate to the fluid is convection. So for the heat is transferred from the plate to the fluid molecules just adjacent to the plate, that is purely by conduction. So this is very important, this concept. Okay, that is mode of heat transfer from plate to fluid adjacent molecules. Okay, adjacent molecules is purely conduction. Okay, so here this Q will be what? If I am having my temperature profile like this, so if this is the axis and my temperature profile is like this, so here it is T infinity, and here it is Ts. So at y equal to 0, if this is my y, sorry, so if this is x and this is y, okay, so at y equal to 0, my slope of the temperature uh, profile is this, and it is dt dy, and at y equal to 0, and conduction is given by the Fourier's law. So then I can write that this q is equal to minus k of fluid del T del y at y equal to 0, right. So and also this q is what? This q I can write as, h delta t, some delta t. So basically here it is the flat plate, so this delta t is nothing but Ts minus T infinity, and will consider, and h is the heat transfer coefficient. Okay, so this is equal to minus kf delta t delta y at y equal to 0. So let me now apply the order of magnitude analysis on this equation. So the order of this equation, this term will be some h into delta Tc, and here also the order will be kf into some delta Tc into delta t, by delta t. So this delta Tc will be cancelled out, and h delta t by kf, this is of the order of 1. Okay. So now I have for Prandtl number less than 1 delta t as this. So let me write it for PR mass less than 1, delta t by L is equal to PR to the power half RE to the power, not half, minus half. Okay. So H delta t by K is H by Kf delta t by L into L by delta t, right, and this is I can write as HL by Kf am I doing the right thing? Okay, so here I have written an extra delta t, right. Okay, and this is correct. I have multiplied an L here and an L here. So this is delta t by L, and delta t by L we know as, so this is HL by Kf. Okay, so I should do it in another way. So let me first tell you a very interesting non-dimensional number. Okay, so what I should do is, okay, do a thing, that is, let me define some variable theta as t minus t wall, that is t surface, by, okay, so t minus t infinity by Ts minus T infinity is my theta, and eta as y by delta t. Okay, or y by L actually, y by L. So if you substitute in this energy balance equation, then you will get, so H T minus Ts minus T infinity, that is equal to minus K del T by del y at y equal to 0. This was the energy balance. So this will be what? H into theta into, okay, okay, so this is T minus T infinity. Okay, so this will be this T is the flat plate temperature. Okay, so this will be H into theta into Ts minus T infinity, right. This will be equal to this kf, and this will be del theta del eta. Now you should be comfortable with this. How I can write this? This will be Ts minus T infinity, and this will be L, right, at eta equal to 0. So this will be cancelled out, right. So then this delta theta by delta eta at is equal to 0, right. So this is a measure of some non-dimensional number h L by kf, and here another factor is coming as theta. That is because I haven't non-dimensionalized it in a correct way. Okay, so and this is coming. Okay, so this is a measure of non-dimensional temperature gradient. Temperature gradient. Okay, so what you can say is that, see, this HL by kf, you can write it as what, L by kf into A by 1 by HA, right. So it is conduction resistance by convection resistance, or conduction or convection by conduction. So how much heat is conducted from the plate? Not only from the plate, how much heat is conducted through the fluid, and how much heat is convected by the fluid. I mean the conduction resistance by convection resistance. So if you want to represent it in terms of the heat fluxes, then it is the convection by conduction, because convection is 1 by convection. I mean more is the convection resistance, the lesser will be the convection, and more is the conduction resistance, the lesser will be the conduction. So this is convection by conduction, right. So how much heat is convected by the fluid, and how much heat is conducted through the fluid. So that is called the Nusselt number. So this is called Nusselt number, and this is very important. In every problem in heat transfer, in convection heat transfer, we will calculate this. So this is Nu. Okay. Now let us go back to this thing. So now if I have to calculate this Nu for Prandtl number much less than 1, so then it is HL by Kf NuL based on L. This L is the characteristic length, and here it is the length of the plate. So this will be H by Kf, I can write, so delta T into L by delta T, and L by delta T we know Prandtl number into Reynolds number whole to the power half, and this is of the order of 1. So this NuL, this will be of the order of Prandtl number whole to the power half and Reynolds number whole to the power half for Prandtl number much less than 1. So this you have to remember. This is very important. Okay. And what you can do is you can see it like this also, that you are non-dimensionalizing it like this. So here this delta T, okay, so this is actually scaling with what, this Ts minus T infinity. So here it will be, so here there will be no theta. Okay, so what we should do is I should do the non-dimensionalization in another way. So let me show you. So theta is equal to t infinity, so t minus ts. So that was mathematically wrong. So let us see it in a better way. Okay. So here theta is equal to t minus t infinity, right, and eta is equal to y by L. So then the main equation is this, okay, t minus t infinity, this is equal to minus kf into del t by del y at y equal to 0, and this is also at y equal to 0. So this is at t at y equal to 0, right, because here t is a variable. So h of ts minus t infinity, right, is equal to minus kf del theta del y del eta at eta equal to 0, and here it will be ts minus t infinity by L, right. So now it cancels out and we can directly get HL by KF is equal to minus this. So this is the Nusselt number. Okay. So now if this is okay, okay, so I have done a mistake here also. This will be the non-dimensionless. So this is Ts minus T infinity. Okay, and here it will be what? So I can write this as theta into this, right, and so this at y equal to 0, this will be theta at y equal to 0, and theta at y equal to 0 is what? So at y equal to 0 t is ts, that means theta is 1, so this term is 1. So this becomes this t minus t infinity at y equal to 0, this becomes ts minus t infinity directly, right. So I hope this is clear to you. This was important. Okay, I have done a mistake in non-dimensionalization here. Okay, I think I have, okay, so I did not make any mistake in defining the variable, but in the mathematics. So here it will be theta into ts minus t infinity, but at y equal to 0 this theta is 1, so here this theta will not be there. Okay, so this should be the approach. I mean, when you are not getting the things, don't just, I mean, accept that okay, I am making some mistakes, so this must be the thing. You should always go into the detailed mathematics and the detailed physics to figure it out, that that what mistake I am doing. Because as I have told in my several of videos, that if you are someone who is trying to go for MTech or PhD or in any research organization, then you have to face this kind of basic questions. So if you don't build your mentality like this to approach everything from the most basic step, and not to accept any illogical thing, then you will be able to crack those interviews, and also in your future life this will benefit you. Okay, so now I think already this discussion has been uh, a very long one, so let us continue the next case, that is for the Prandtl number greater than 1 in the next discussion, and we will also see the integral method and the similarity solution. So I will suggest you to just recapitulate the similarity solution and the momentum integral solution, okay, for the boundary, for the hydrodynamic boundary layer that I have taught earlier. So, and that will help you in the future discussions, and until then let us say goodbye. And obviously, needless to say that you put your suggestions and comments, and if you need anything in the comment box, you should put it, and I will obviously go through that. So goodbye and take care.